Welcome, Calculus fans, a video on logarithms, exponentials, and other inverses. And in this video, we're talking about general exponentials and logarithms. So we'll start with some definitions, how to define our general exponent and our general logarithm. We'll get into some particulars on the calculus of those functions, and then we'll spend a little bit of time talking about limits. We saw last section when we defined the natural exponential function that for any value a that's greater than 0, e to the natural log of a is equal to a. So we'll use this framework to define the general logarithm and the general exponential. So let's talk first about the general exponential. Here's a definition. Whenever x is any real number and a is a positive number, we will define a to the x as e to the ln of a to the x, which we can therefore rewrite as e to the x ln a. That's a trick of logarithms. And rewrite that as e to the ln a x. So at the end of the day, the general exponential a to the x is equivalent to a specific natural exponential, where the argument of that exponential is given by ln a times x. This is a common thing that we're going to do, that is going back and forth between a to the x and e to the ln a times x. And the key to this transformation is the fact that a is just a constant, a positive number. So we can use the chain rule, therefore, to identify the derivative of this general exponential function. We'll start by expressing a to the x as e to the ln a times x. So since we can write a to the x as an exponential, we can take the derivative, and we know how to differentiate exponential functions. So the derivative of e to the stuff is e to the stuff times the derivative of the stuff. When a is a constant, ln a is a constant too, and the derivative of a constant times x is just that constant. Now, of course, we can recover a to the x from e to the ln a times x, and we see that the derivative is exactly a to the x ln a. So here's our first derivative rule for general exponential functions. The base derivative of an exponential function a to the x is a to the x ln a. And of course, if there's a chain rule like a to the u, the derivative is a to the u ln a times the derivative of u du dx. Fairly straightforward, just based on the relationship between the general exponential and the natural exponential. Okay, let's go ahead and find the derivative of this function, 2 to the x plus x squared. Now, when you look at this, the new player in town is the 2 to the x, and we know how to differentiate x squared. So the derivative is quickly written as 2 to the x ln 2 plus x squared. So we see that derivative, 2 to the x ln 2 plus 2x, and this is our first experience with the difference between exponential functions and power functions. In this case, the exponential function is 2 to the x. The power function is x squared. Here's another example. Let's find the derivative of 3 to the minus x plus x to the minus 3. Now, similarly here, we know how to differentiate x to the minus 3. Differentiating 3 to the minus x is a little bit different, so let's check that out. So we see the derivative of x to the minus 3, and the derivative of 3 to the minus x requires a chain rule, taking 3 to the minus x times the natural log of 3 times the derivative of minus x, which of course is just minus 1. The derivative g prime is minus 3 to the minus x times the natural log of 3 minus 3 times x to the minus 4th. And here's our second example, illustrating the difference between exponential functions and power functions. In this case, the power function is x to the minus 3. The exponential function is 3 to the minus x. Now that same relationship can be used to determine the graph of f of x equals a to the x. Let's have a look here. Remember that a is a constant, and then the natural log of a is positive when a is greater than 0. The natural log of a is negative when a is between 0 and 1. Now, The graph of e to the ks is what I'm going to call an increasing exponential. It goes like this. And similarly, the graph of e to the minus kx is a decreasing exponential. So that's really all there is for a to the x also. When a is between 0 and 1, we get a decreasing exponential. And when a is greater than 1, we have an increasing exponential. So here are those graphs, a greater than 1 and a between 0 and 1. Now, of course, again, those general exponential functions a to the x are just natural exponential functions in disguise. So as long as we know how to graph the natural exponential function, we can graph the general exponential function too. Let's have a look at another example. Let's find the equation of the line tangent to y equals 2 to the x at x equals 0. Well, we can see that the point in question here is, of course, x equals 0 and y equals 1. Now, of course, the slope is just given by the derivative evaluated at the point. In this case, the equation of the line is y equals 1 plus natural log of 2 times x. Now, we know natural log of 2 is the natural log of a number that's between 0 and e, so it's going to be less than 1. It turns out it's like 0.6 something something something, so this is a line with slope that's less than 1. Let's go ahead and have a look at the line tangent to this graph, y equals 2 to the minus x at x equals 0. Similarly, the point in question is 0, 1, and similarly, the derivative gives us the slope. So in this case, the slope of that line is minus log of 2, and the equation of the line is given by 1 minus log 2 times x. One more quick comment. So the graph of the natural exponential is special. Here's that graph, and we saw in our last video that the equation of the line here is y equals x plus 1. That line with slope 1 is the only exponential function who has slope 1 at 0. And we talked about this a little bit last time. That's what's special about the natural exponential function. With every derivative comes an antiderivative rule, and here is the antiderivative of the general exponential function. The general antiderivative of a to the x dx is 1 over natural log of a times a to the x plus a constant. Let's go ahead and have a look at this integral. We can see that the fundamental theorem of calculus and this general antiderivative formula gives us the general antiderivative of this exponential function. In this case, the value of the definite integral is 3 to the 4th minus 1 over the natural log of 3. I mentioned this before, but I want to put it right out there in its very own slide. Power functions and exponential functions are different. It's a common calculus student mistake to get these confused, so don't do that. The derivative of the power function x to the n is n times x to the n minus 1, and the derivative of the exponential function a to the x is a to the x times the natural log of a. You can see that those are different. The functions come in different forms and the derivatives are different too. So make sure that you keep those straight in your mind. Now, one thing that might happen is there might be a function that's a mix of both. So here we see a function u that is has x's in the base and x's in the exponent. So it turns out we have to use that e to the ln trick to find the derivative of this function as well. So let's check it out. So rewriting x to the x as e to the ln x to the x, we can hop that power of x down and rewrite it as e to the x ln x. Then the derivative just comes from the chain rule. So the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And when you go to take the derivative of the stuff, there's a product rule involved, and here we've evaluated the product rule. Now, of course, e to the x ln x, if you track it backward, just came from u of x, which is x to the x. So we see here that the derivative is x to the x times the natural log of x plus 1. So again, when you have mixes of power and exponential functions, go ahead and use the e to the ln trick to rewrite that as an exponential function with a composition in the argument. Okay, let's go ahead and talk about the general logarithm. As you might imagine, the graph of a to the x passes the horizontal line test. Here we see a to the x when a is greater than 1. So we can talk about the corresponding inverse function. We'll go ahead and define that inverse function. Again, graphs here are for a greater than 1. The inverse function is the log base a of x. So here are our inverse relationships. Log base a of a to the x is x for all x, and a to the log base a of x is x when x is a positive number. Here are known values. A to the 0 is 1, so log base a of 1 is 0. A to the 1 is a, so log base a of a is just 1. And finally, the end behavior on this graph, the limit as x goes to infinity of log base a of x is infinity, and the limit as x goes to 0 from the right of log base a of x is minus infinity. And still, these are for values a greater than 1. We can also find the derivative of this general logarithmic function. And the derivative of the general logarithmic function comes from the change of base formula. Here's the change of base formula. Log base a of x is the quotient, natural log of x, divided by natural log of a. This is a really quick derivation that you can use if you're in a pinch, so I'll go through it. So we start with an equation y equals log base a of x. Now the inverse relationship implied by that, the exponential relationship, is a to the y equals x. Now of course we can introduce a logarithm on both sides, a natural logarithm, by writing log a to the y is log of x. Use our hop it down rule of logarithms to write this as y times log a is log x, and rewrite y as natural log of x divided by natural log of a. Since we started with the two with y as log base a of x, we can see that log base a of x is natural log of x over natural log of a. This tells us the derivative. The derivative is just these should be ln's, not logs, so let me fix those. Okay, I'll fix the logs there in red should be natural logs. And we can see that the derivative of the log base a of x can be written as the derivative of the quotient of those two logarithms, log of a divided by natural log of x. Now, of course, natural log of a is just a constant, so we see that the derivative here is 1 over the natural log of a times 1 over x. The chain rule follows the same way. However, it's usually easiest just to rewrite our general logarithm as a natural logarithm using the change of base formula. So we'll see this in an example coming up next. Okay, here's the example. Let's go ahead and find the derivative of this function log base 8 of 2 plus x. We'll start by rewriting f of x as a natural log using the change of base formula. In this case, using that change of base formula gives us f of x is natural log of 2 plus sine x divided by natural log of 8. Now, of course, natural log of 8 is just a constant, so we can pull it out front. The derivative of natural log involving a composition is 1 over the inside function times the derivative of the inside function. And of course, the derivative of 2 plus sine of x is just cosine of x. Okay, let's go ahead and have a look at some limits. The limits involving these functions are based on the fact that the derivative of the natural log function is 1 over x. So f prime of 1 when f of x is natural log of x is equal to 1. So we can use the calculus 1 definition of the derivative. Remember that thing? F prime of 1 is the limit as h goes to 0 of f of 1 plus h minus f of 1 over h. Of course, in this case, f of 1 plus h is natural log of 1 plus h. F of 1 is just natural log of 1, which we know is 0. And we can express this as the limit as h goes to 0 of the natural log of 1 plus h. So here's a new limit that we can write in terms of the natural log. Using, again, that hop it up trick for the natural log, we see that the limit as h goes to 0 of natural log of 1 plus h to the 1 over h is equal to 1. Now, of course, due to continuity of the natural log function, we can see that the limit as h goes to 0 of 1 plus h to the 1 over h is equal to e. So this is our new limit, and I'm going to write it with some x's in it instead. The new limit is the limit as x goes to 0 of 1 plus x to the 1 over x is equal to e. We can rewrite this slightly with the substitution. So here we've used the substitution t equals 1 over x, or equivalently, x equals 1 over t. We can see that in t world, that limit can be expressed as the limit as t goes to infinity of 1 plus 1 over t to the t power, and that limit had better be the same as it was before, which is exactly e. So here's the second limit to know, the first one really written the different way. The limit as t goes to infinity of 1 plus 1 over t to the t power is equal to e. So we can manipulate limits using these new limits. Here's an example. Let's have a look at the limit as x goes to infinity of 1 plus 2 over x to the 7x power. Now, we don't know anything about limits involving 2 over x, but we do know things about limits involving 1 over x. So that suggests a substitution, x, 2 over x equals 1 over t. We can see that with that substitution, 2 over x equals 1 over t, that x is 2t, and when x goes to infinity, t does too. So let's go ahead and rewrite our original limit in t world. So here we see that limit in t world, the limit as t goes to infinity, 1 plus 1 over t to the 7 times 2t power. Now, of course, we can simplify the 7 times 2t power to write it as 14t. And due to continuity of power functions, we can express this as the limit as t goes to infinity of 1 plus 1 over t to the t power, all raised to the 14th power. Now, of course, the stuff inside is exactly e, so the answer here is e to the 14. Okay, folks, hope you've enjoyed this video on general exponential and logarithmic functions, limits. Have a great day, and we'll see you next time. Bye-bye.